My name is Jason Cerundolo. I'm the CEO and co-founder here at Colossus. And we got started with this company about 5 years ago or so. And the problem that we saw that we identified in the market was a severe lack of computing power that was available. I like to describe it as thinking back to the 1990s when if you wanted to meet up with your friend at the mall, you'd have to call their house on a landline and hope they pick up, arrange a time to meet, and then if something went wrong, better luck next time. You're out of luck. And these days, of course, you just pick up your smartphone, you'd send a text, you'd share your location, come up with a new plan on the fly, that sort of thing. And so that's really the kind of the difference in computing that we were seeing in the market. Part of the inspiration for the company was seeing the Ingenuity helicopter fly on Mars, and just due to the fact that it's barely possible to fly on Mars with the gravity in the atmosphere, uh, they had to do a lot of work to reduce the mass but maintain the capabilities of the helicopter. And one of the ways that they did that was for the navigation system, they used an unmodified cell phone grade processor. It's an industrial temp range Snapdragon that did the visual odometry. And so seeing that flying on Mars and seeing what was possible versus the Perseverance rover that was monitoring it was using a Rad 750, which, if you'll remember, is the big, colorful iMac processor back from 1998. So literally, 1990s tech versus modern cell phone tech. And yeah, when I went to look through the market and see what was available, I could find a lot of flight computers or OBCs, kind of to manage your satellite, to maybe act as a payload controller, flip some circuit breakers on and off, that sort of thing. But to really do serious computing on board the satellite, that was what was missing from the market. So that's what we wanted to focus on, was really bring all the capabilities that you're used to these days. Your smartphone that's backed up by giant data centers doing all the processing to support all the applications on your phone, and bring that to the space environment. So it's really taking the last like 40 years of development in data centers and applying that to spacecraft.
So, and presumably, so that's very much kind of, we're on the edge of the networks here. What are the kind of the main challenges, though, that you're having to overcome? The differences between doing it here on Earth and doing it on the moon or on Mars or orbiting.
Right. Yeah. So the two big ones. The first one is just the remote location of it. Here on Earth, if SSD fails, a little red light flips on, and then a tech comes in next week and just swaps out the module. That's not really an option on anything other than maybe ISS right now in space. And so reliability is a big concern there. And then the other big difference between computing on Earth and in space might be obvious to some, is the radiation environment. So even in LEO, you get protons, charged particles, cosmic rays coming in. And so there's a bunch of different types of radiation that can cause many types of problems. So we're designing our hardware to be resilient against those types of effects, and really just kind of extend the same level of reliability, or what's called high availability on Earth. Take the same approach that, say, like Facebook has, where it's a news event if their system's down for 3 minutes in a day. And the way that they do that is not by having computers that never fail. It's by having a system that can deal with failures and work around them.
Okay, so does that mean it's more than just a hardware problem? This radiation thing, it's more than just a material science problem. Is there other stuff going on as well? Maybe to explain the hardware thing and the software and systems part of it.
Mm-hmm. Yeah, the way that I describe it is that we're designing reliability in at a systems level. And so that encompasses hardware, software, operations. So it's not just one magic material that makes everything better. This is in contrast to the traditional approach, which is you use very old, giant silicon that's radiation hard by design, that's maybe 20, 30, 40 years old. and you put it in big ceramic cases and put that in a giant box with a lot of shielding, and then you have a very stable hardware platform that is basically immune to radiation. Then you can write whatever software you want on top of that. But the downside then is, you're using tech that's 10,000, 100,000 times less performant, and it's really big and heavy and power hungry. So our approach is to use the modern processors, but of course they're not as inherently immune to radiation, and so we design in protections at the hardware level. So it starts with careful selection of our components to make sure we're sourcing components that are going to behave well in the radiation environment. We actually do extensive radiation testing with proton beams and heavy ion beams on Earth to characterize those performances. Then on top of that, we also design protection circuitry into our systems so that if there is a failure, it's mitigated. So for example, current limiting E-fuses that can mitigate the effects of a latch up and prevent permanent damage from occurring. And then a telemetry system that can detect those and reset the system and get it back working. And then at a software level, it's designing the software to be resilient against failures. So have multiple copies of the bootloader, have multiple copies of the software that can run, have error correction codes built in so that we can detect bit flips and either use a backup file or just correct the errors on the fly. And then at a systems level, it's designing our systems much like you have servers on Earth here, where you can combine multiple units together and have them work as one big system, where if everything's going great, then you have multiple times the performance. But if one of the units has a problem, the other units can detect that, reassign work, keep functioning while the other unit is rebooting. So it's not a all or nothing.
Sure. Okay. And so, I mean, it sounds like one of these things when you're operating in space, particularly for science missions or any kind of data collection, this sort of thing is almost a no-brainer. So, is there a choice though? Like, why would people choose you, and what are the alternatives? Is yours kind of like a premium product if they're going for a super high-end project, as opposed to a slightly less sophisticated product, for example? And what is it that you actually provide? Is it just a box with data with microchips that you've just described and all that sort of stuff? Like, maybe talk us through the kind of the alternatives, the options, and what it is that actually people are purchasing from you.
Mm-hmm. Yeah, what people are purchasing from us is really a solution to their problem. So it's a computing system that solves their problem, that is a reliable component that can interface with the rest of their satellite, with their sensors, their imagers, whatever they have, and their spacecraft bus. And really that's in contrast to kind of more of a DIY approach. That's definitely where I was at before I started this company, was having to build some of these systems on my own, just because they simply didn't exist in the market. So if you're going that route, you have to select components or maybe build your own circuit boards, design the enclosure, write all the software, all the drivers, all the low-level code to get it operational, and modify the operating system to account for all of that. And so at that point, the costs add up. It can take a lot of time and energy to do that. So what we offer to our customers basically is a shortcut where they can get up and running in a matter of a few weeks or a few months versus spending years hiring a team to do it themselves. In terms of the actual hardware that we deliver, so we deliver for our computing products. It's a system that's ready to go out of the box. You plug our unit in with power and Ethernet, and you get a terminal prompt, and it's just like any other Linux machine developers might be familiar with. So just like opening up a new laptop, you know, boot it up, install your software, and you're ready to go.
Okay, and I think you've got one product that I'm aware of at the moment called Kestrel. Maybe you could maybe talk us through some of the details of that, maybe some of the surprising things in there that people might not be aware of, but also maybe talk to how that will be one part of a bigger family of kind of solutions that you're kind of aiming for.
Mm-hmm. Yeah, I'd actually like to talk about Falcon, if I might.
Sure.
That's yeah, Falcon's our latest generation GPU. I actually have a model of it here. So just to give you an idea of the size and shape of it. So what this is a data processor based around the NVIDIA Orin AGX GPU. And what we've done is add a custom carrier board that provides the projection circuitry, all the interface electronics, some other features like mass storage, everything that you need to turn it from a module that needs a custom circuit board into a system that's ready to go that you just bolt down to your spacecraft and plug in. So some of the features that we've added that provide a lot of flexibility is the option for add-on boards. So this is similar to if you've ever built your own gaming PC and you want to swap out your graphics card and you just pull that card out and put a new one in. We have pretty much the same functionality with Falcon, where it's the same protocol, it's PCIe, but it's a different form factor, obviously. But that provides an extensible interface for adding new connectivity features, connecting to different image sensors, for example, adding extra processing. So we have a library of add-on boards right now that support things like extra Ethernet ports. We have one with an FPGA that can support a wide range of protocols like SpaceWire, CameraLink, generic LVDS, high-speed systems like PCIe or 10 gigabit Ethernet. And then we have another one that has a PCIe switch on it that can support a bunch of PCIe cameras, which is another popular protocol for some of these payloads. So that provides a lot of options for connecting the data processor directly with something like an image sensor that's generating a huge amount of data that would be hard to route through kind of traditional spacecraft systems. And then that's just the start, though. We've also announced another product called Razorback. That's our Ethernet switch. So similar to, you're setting up your gaming rig and you want to plug in your printer and your scanner and your desktop and your laptop, and you just need like an 8-port Ethernet switch. We noticed a similar need on the spacecraft side, where more and more systems are moving towards Ethernet. So cameras, computers, OBCs, and there's just a need to connect a bunch of these systems together. So this is Razorback's a standalone Ethernet switch. It has a few extra features compared to a simple switch. It's got some layer 3 managed switch capabilities. So it can do some sophisticated stuff like segregating networks based on VLAN. It supports time-sensitive networking and kind of all the modern Ethernet networking features that you'd expect, and provides that in a small package that's ready to go for integration into a spacecraft.
Great. And so who is the kind of the ideal customer of this kind of system? Are there particular industries or projects that would benefit from this kind of thing in space?
Yeah, our primary customers are one of two, either spacecraft integrators or payload integrators. So we have some customers now who are purchasing our computers. They'll purchase cameras from other vendors, plug all that together, and then write their own software to do tasks like space situational awareness or rendezvous and proximity operations. We also have Earth observation customers that are dealing with really latency sensitive applications where microseconds or milliseconds can matter. So really, I kind of view it as two different use cases. There's the large amount of data that's generated by these sensors. And so being able to at least do some filtering or early processing on board can significantly reduce the amount of data that's sent down, sometimes by a factor of 10 to 1. And then the other use case really is latency sensitive applications where you need to be able to do the processing on board. It's like I was talking about rendezvous and proximity operations and docking. You need a real-time computer to be able to see the other spacecraft, estimate its pose, how you're going to do the approach, monitor everything, keep that safe. And you can't really do that without some sort of computing on board. And if you're relying on sending all the data down to the ground to get processed and then send commands back up, it might be too late. The analogy I use is like during the Apollo program, there was a transposition and docking maneuver, and My joke is that we had an onboard computer. It was called the command module pilot, and he would just stick his head out the window and use the stick to get the spacecraft docked safely.
Right.
And
And
now we have now
you
we have
mentioned
electronic computers.
sure. So you mentioned your Falcon is kind of the big brother of Kestrel. How do those two
Mm-hmm.
products? What's been the evolutionary journey between Kestrel and Falcon, and what are the improvements? Why did you make them? Have there been any trade-offs?
Mm-hmm. Yeah, so but the big improvement is at least in terms of AI performance, Falcon's about 200 times the performance of Kestrel. So it's significant increase in computing power. One of the trade-offs there is, as you might imagine, is an increase in the electrical power, but it's 200 times the AI performance for about 4 times the electrical power consumption. So it's much more efficient. However, the power consumption is increased. The physical size of the units increased. But this is really tracking an industry-wide trend that we're seeing towards larger satellites. So Kestrel is a PC-104 form factor. It was really designed for small CubeSat missions and maybe down to like a 6U form factor. But nowadays, the more popular class is ESPA class, or kind of that 50 to 200 kilogram range. And then we're even seeing satellites get even larger than that, up to like 1 or 2 tons. And with the increased size of the satellite, there's a lot more electrical power, a lot more thermal handling capability available. And so that has also led to, say, larger sensors that are generating more data. And so the computing needs have increased substantially as well. So that's part of what motivated us to follow that trend and develop larger, higher performance capability.
And is AI usage in space another emerging trend that you're seeing? I mean, what are the kind of the demands you're getting from clients, or the questions that they're asking about the sorts of things they might be thinking
Mhm.
about?
Yeah, so it's AI, but not necessarily LLMs. It's AI is a broad category there.
Mm-hmm.
But a lot of the processing that we're seeing our customers do is really based on image processing, just because you start to add up how many pixels across and up you have times bit depth times frame rate. And we have customers that are processing data on the order of tens of gigabits per second of data. And I don't know about you, but like my home internet is pretty good, but it's only 1 gigabit per second.
Mm.
It's not exactly a one-to-one comparison, but it just gives you an idea how much data is being generated by modern sensors. And kind of overall rule of thumb for these sorts of image processing pipelines is you want to throw away as many pixels as you can as fast as you can.
Mm-hmm.
And so that's where our units can come in to do things like windowing, where you just chunk out the interesting part of the image and throw away everything else. No sense downlinking blank sections of the image. But we do have customers that are doing more sophisticated processing based on that. So they'll do that pre-processing to reduce the data, then put that through the GPU. Then they have their own algorithms. So some examples there is performing a pose estimation of a client spacecraft to estimate what direction it's facing. Like, are we lined up for the approach? That sort of thing. And then on the Earth observation front, there's a lot of use of other types of AI to do things like classification. So one example there would be ship detection, where if you were to just take images of the entire Pacific Ocean, I mean that's half the planet right there. That's going to be a huge amount of data. But with the onboard processing, you can kind of look at each image as it comes through and run a simple AI model, see if there's a ship there, get some basic information about it, and then compare that even against AIS data, like radio data, to see if this ship is broadcasting its location like it should be. And if it's not, that might be indication that someone should take a closer look. And you can do all that on board and then just send basically the summary down to the ground. And it's a factor of 1,000, 10,000 to 1 in terms of the data savings.
Wow, great. And so if somebody wanted to use a Falcon on their project, what's the kind of process of dealing with you? Like you made it sound very simple earlier. It's almost like a plug
Mhm.
and play kind of system. But what kind of onboarding is there? What information do you need from them to set this up for them?
Yeah, so what we've seen, our most successful customers are already running their software on GPUs on the ground here, and they already have a pretty good idea of what they want to do, but they just need help with the hardware to do that in space. So that's our sweet spot. What we would recommend is get in touch with us. Sales at colossuscompute.com will work. We also have our website where you can fill out a small form there. We've also put a lot of our technical documentation available for free up on our website. A lot of our documents, like say our interface control document or ICD, that's available for download without an NDA. One of the things, speaking as an engineer by background, I want to make sure that the other engineers out there have the information that they need to make informed decisions about, is this unit going to work, or is this going to be a good fit for any given application. So that would be my recommendation to start, is review the technical documentation that's out there, get in touch. We're happy to answer any questions that you have. And then in terms of the sales process, it's really a discussion about the customer's mission, their needs, timelines, and then the only other part is whether you can use some of our existing hardware, or do we need to talk about some potential customization to make the mission work. But we're here to help.
Great. Brilliant. Jason, thanks very